These are the practice problems for Algebra 1, Unit 5, Lesson 13. This will be the last lesson before the mid-Unit 5 test, which will be Monday. Here is a graph of P, an insect population, W weeks after it was first measured. The population grows exponentially. Number 1, what is the weekly factor of growth for the insect population? So here's what we know. After 1 week, the population was 900. 2 weeks later, it was 8,100. So we need to figure what we can multiply each time to go from 900 to 8,100. So obviously multiplying by 1 each time doesn't change the number. So let's try 2. If we multiply by 2, this becomes 1,800. And if we multiply by 2 again, this becomes 3,600. So 2 is not high enough. Now let's try 3. 900 times 3 is 2,700. And 2,700 times 3 is 8,100. So, for number 1, the weekly factor growth is 3. Number 2, what was the population when it was first measured? Well, if we're multiplying by 3 as we move to the right, we're going to multiply by the inverse to go left. So we could say 900 times 1/3, and that equals 300. So the population, when it was first measured, was 300. Number 3, write an equation relating P and W. P is our output, so we're going to write P of W because W is our input. This is an exponential function because we're multiplying by the same amount each time. So we're going to start with our y-intercept, which we set in number 2, is 300. Then we're going to multiply that by the growth factor, which we set in number 1, was 3. And that growth factor of 3 is going to have the exponent of the input, which is W. If you have any questions about how I answered this practice problem, please use class time now to ask for further clarification. Here's a graph of the function f defined by f of x equals a times b to the power of x. Select all possible values of b. So first, we need to remember b is the growth factor. The graph shows that this is decreasing. In order for this to decrease, b must be less than 1. So if we know that b must be less than 1, as we look through the choices, we're going to ask, does it make sense? So choice A is 0. If I put 0 in for B, then anything times 0 becomes 0, and this line would be all the way down at the x-axis. So it cannot be A. Choice B is 1/10. 1/10 is less than 1, and it would allow for a decreasing graph. So B would be a possible value. Next is choice C. This is 1/2. 1/2 is less than 1, so that could be a value. Then we look at D. D is 9/10. That's less than 1, so that is also a possible value. Choice E is 1, and if this were 1, then multiplying by 1 would always end up with the same y value, and you would have a horizontal line where you started at the y-intercept. So E could not be the answer. Choice F is 1.3. 1.3 is greater than 1. So if we were to multiply by that over and over, the graph of our line would be going up, not down. So F could not be an answer. And lastly, choice G is 18/5, which is also 3 3/5. That's greater than 1. So again, this graph would be going up, not down. So G cannot be the answer. So one thing we see that we could add here is that B is less than 1 and B cannot equal 0 because then we wouldn't have a graph. 0 to the power of 0 would be 1 because anything to the power of 0 is 1. So we would have our initial y-intercept, but then we would immediately go to 0 and we would stay there. So the correct choices on this one are B, C, and D because they are all greater than 0 but less than 1. If you have any questions about how I worked this practice problem, please use class time now to ask for further clarification. The function f is given by f of x equals 50 times 1/2 to the power of x, and the function g is given by g of x equals 50 times 1/3 to the power of x. Here are graphs of f and g. Kieran says that since 3 is greater than 2, the graph of g lies above the graph of f. So graph 1 is the graph of g, and graph 2 is the graph of f. Do you agree? Explain your reasoning. So Kieran is correct that 3 is greater than 2, but we do not have 3 and 2. We have 1/3 and 1/2. And 1/3 is less than 1/2. So what we're saying here is that when they start in the same place at 50, f is going to keep half of its value each time, but g is only going to keep 1/3 of its value each time. And since 1/3 is less than 1/2, graph 2 is going to be g of x, and graph 1 is going to be f of x. So to answer their question, no, because we don't have factors of 3 and 2. We have factors of 1/3 and 1/2, and 1/3 is less than 1/2. Graph 1 is f of x, and graph 2 is g of x. If you have any questions about how I solved this practice problem, please use class time now to ask for further clarification. The function f is defined by f of x equals 50 times 3 to the power of x. The function g is defined by g of x equals a times b to the power of x. Here are the graphs of f and g. Number 1, how does a compare to 50? Explain how you know. So f of x is the red line, and we see that it is lower than the starting point of g, which would be a. So that means a must be greater than 50 because the y-intercept for g of x is higher than for f of x. And number 2, how does b compare to 3? Explain how you know. What we notice is that f of x grows quicker than g of x does. And if the growth factor for f is 3, and that growth factor is larger than the growth factor for g, then b must be less than 3 because g of x is growing slower than f of x. If you have any questions about how I solved this practice problem, please use class time now to ask for further clarification. A ball was dropped from a height of 150 centimeters. The rebound factor of the ball is 0.8. About how high in centimeters did the ball go after the third bounce? So this is going to be an exponential function. We know that our starting point was 150 centimeters. We know that our growth factor is 0.8, and we know that we are on the third bounce. So now we can use a calculator, and we have 150 times, in parentheses, 0.8 to the power of 3, and close our parentheses. Then we hit equal, and that's 76.8, which means A is our correct choice. If you have any questions about how I solved this practice problem, please use class time now to ask for further clarification. The dollar value of a car is a function f of the number of years t since the car was purchased. The function is defined by the equation f of t equals 12,000 times 3 over 4 to the power of t. Number 1. How much was the car worth when it was purchased? Explain how you know. We can look at the function, and the number by itself is the y-intercept, and the original worth when it was purchased is the y-intercept. So we can say $12,000 because that's the y-intercept. Number 2. What is f of 2? What does this tell you about the car? So f of 2 would be 12,000 times 3 over 4 to the power of 2. 3 divided by 4 is 0.75, and 0.75 squared is 0.5625. Now we multiply that by the original value of 12,000, and we get a value of $6,750. And that's $6,750 after 2 years. Number 3, sketch a graph of the function f. To do this, I have typed our function into the Desmos.com graphing calculator. You can see that it starts at the y-intercept of 12,000, and it's maintaining 3/4 of the value every year. Number 4. About when was the car worth $6,000? Explain how you know. If we look at the graph, the y-axis is the value. So we find 6,000 on the y-axis. We come over until we hit the line, and we can see we hit the line where the x value is 2.4. So the car was worth $6,000 approximately 2.4 years after purchase. And we can see that that makes sense because in number 2, we said that after 2 years, the value was 6,750. So in the next zero point 0.4 years, we lost another $750 of value. If you have any questions about how I solved this practice problem, please use class time now to ask for further clarification. The equation y equals 600,000 times 1.055 to the power of t represents the population of a country t decades after the year 2000. Use graphing technology to graph the equation. Then set the graphing window so that you can simultaneously see points on the graph representing the population predicted by the model in 1980 and in the year 2020. What graphing window did you use? So first I went ahead and I typed in this equation into the Desmos.com calculator. And we got this blue line right here. Now, one thing to know, we need to see 1980 and 2020. So 1980, if T represents the population decades after, then 1980 is going to be 2 decades before. And 2020 is going to be 2 decades after. So I need 2000 is going to be my x. So I need -2 less than or equal to x less than or equal to +2. Next, we need to decide on a graphing window for the y-axis. So if we look, we know that our lowest is going to be down here when x is -2. And we can see that the value is approximately 539,000. So we could pick a bottom of 530,000. So we'll say 530,000 less than or equal to y less than or equal to. Now we need to find the top end of the range. We know that that's over here to the right where x equals 2. And we see that our value is approximately 667,000. So we could choose 670,000 to be able to get all of those values in. So our graphing windows, the x's would be -2 to 2 because we're wanting 1980, which is 2 decades before 2000, and we want +2 because 2020 is 2 decades after 2000. For our y values, we want to set a bottom end around 530,000. That way we can get all of the y values at the bottom in the screen. And then we'd want to go up to at least 670,000 so that we can get all of the y values at the top end in the screen. If you have any questions about how I solved this practice problem, please use class time now to ask for further clarification. And our last practice problem for this lesson. A triathlon athlete runs at an average rate of 8.2 miles per hour, swims at an average rate of 2.4 miles per hour, and bikes at an average rate of 16.1 miles per hour. At the end of one training session, during which she did not run, she had swum and biked more than 20 miles in total. Is it possible that she swam and biked for the following amounts of time in that session? Show your reasoning. So A, swam for 0.5 hours. Well, swimming is a rate of 2.4 miles per hour, and that would be multiplied by the 0.5 hours. Then we would add the biking. Biking at an average rate of 16.1 for a total of 1.25 hours. So 2.4 times 0.5 is 1.2. And 16.1 times 1.25 equals 20.125. That's a total of 21.325 miles. And we know she had swum and biked more than 20 miles in total. This is more than 20 miles. So yes, this is a possible combination. B, is it possible they swam for 1/3 of an hour and biked for 70 minutes? Again, swimming is at a rate of 2.4 for 1/3 of an hour. And we're going to add that to the biking, which is a rate of 16.1 miles per hour for 70 minutes, which would be 1 1/6 of an hour. So 2.4 times 1/3 would be 0.8 miles. And 16.1 times 1 1/6, we're going to say 1 divided by 6, and then we're going to add 1 to that. Now we're going to multiply this by the 16.1, and that equals approximately 18.8. And this makes a total of 19.6 miles, which is less than 20 miles. So the answer on this one would be no, because it doesn't meet the standard of more than 20 miles in total. Number 2, write an inequality to represent the relationship between the time she swam and biked in hours and the total distance she traveled. Be sure to specify what each variable represents. So I'm going to put this down here, number 2. We would have 2.4 times S, and S is going to be swimming. So S equals the hours spent swimming. We're going to add that to 16.1, which is the rate they bike. And we're going to multiply that times B. And we're going to say that B equals the hours spent biking. And that will equal capital T, and capital T equals total miles. And number 3, use your inequality to graph a solution set that represents all the possible combinations of swimming and running times that meet the distance constraints regardless of whether the times are realistic. So now we are talking about the constraint where this needs to be greater than 20 miles total. So first off, we're going to rewrite this as 2.4s plus 16.1b is greater than 20. This is in standard form, and standard form is great for finding the intercepts. So first, we can say, what if they did no swimming? We put 0 in for S, and anything times 0 is 0. So no swimming would be 16.1b is greater than 20. Now we're going to divide both sides by 16.1. And that gives us b is greater than approximately 1.2. So on our graph, biking is our y-axis, so we could put our y-intercept at 1.2. Now we're going to say no biking. We put 0 in for B, 16.1 times 0 is 0. So now we have 2.4s is greater than 20. To get s by itself, we're going to divide both sides by 2.4. So now s must be greater than 20 divided by 2.4 equals approximately 8 1/3. So now we can put our x-intercept at 8 1/3. And then when we draw our line to connect them, remember we only want values that are greater than, not greater than or equal to. So this is going to be a dashed line that is connecting them. And then we would shade in everything above because these would be the values that would make this true. So any combination of hours swimming and hours biking in the green shaded area is a solution because it means they did more than 20 miles total. Anything on the dashed line would not be a solution because the dashed line would be exactly 20 miles, and nothing in the unshaded area is a solution because all of those combinations would make it less than 20 miles total. If you have any questions about how I solved this practice problem, or if you have any questions about any of the previous practice problems, please use class time now to ask for clarification. If you have any questions about anything we've gone over in the first half of Unit 5, please use class time to ask for clarification before the test. The test will be Monday.